So why do I call this video Everything You Know About Two's Complement is Wrong? Well, it's because most of the time when you learn Two's Complement, you learn it by rote and you learn it with simple rules. And that's fine, but it doesn't really let you understand what Two's complement is for and why it works the way it does. It's a very clever mathematical representation that lets you see negative and positive numbers in the same representation. But if you don't know why it works this way, then it's hard to understand sometimes. So first, let's show you how people often will teach Two's complement. They'll take a number, like for example, 0, 1, 0, 0, 1, which in binary is 0, 1, 0, 0, 1, and that represents 0 16s, 1, 8, 0 4s, 0 2s, and 1 1 is 9. I'll move it over, is 9. Right? That's how we represent numbers in base 2, right? Each number is a power of 2, just like in base 10, each number is a power of 10, and that makes sense. But how do you figure out this value if it were a negative number? Well, with Two's complement, what they often will tell you is you just flip the bits and add 1. We flip the bits and we add 1 is 0, 1, 0, 0, 1. I've done it wrong. I already flipped the bits. Sorry. Flip the bits, right? And then add 1, which is 1, 0, 1, 1, 1. And then we just say that's negative 9. But why is that negative 9? That doesn't make a lot of sense unless you think about what the representation is supposed to look like, right? We would like to have each of these 1s and 0s represent something, just like they do here. And as it turns out, they do. We just often don't teach it that way. So the way to think about Two's complement that makes a lot more sense than any of the stuff you've seen before is to take the top place value and have this represent a negative value. So say this is negative 16, this is positive 8, this is positive 4, this is positive 2, and this is positive 1. So all of these place values, the bottom most, n minus 1, are positive, but the top one represents a negative value. And if you look at it that way, well, then it makes sense because negative 16 plus 4 is negative 12, plus 2 is negative 10, plus 1 is negative 9. This actually works out, and that makes some kind of sense. So flipping the bits and adding 1 gets you to a representation that actually does make sense if you think of this top bit as equaling a negative place value instead of a positive place value. Now this way of thinking about Two's complement also means that a lot of the other mechanics of Two's complement also make a lot of sense. So let's look at, for example, sign extending. Here's a number that is in Two's complement. Let's look at this number. What does that number represent? Well, this is a 1 and a 2 and a 4 and an 8 and a 16 and a 32 and a 64. So that's 32 plus 16 is 48, plus 1 is 49. Now, in Two's complement, you have to know how many bits are in the representation. That's one of the rules. So in this case, 1, 2, 3, 4, 5, 6, 7 bits. If we wanted to make it 8 bits, we'd have to extend the sign, which in this case is 0, makes it positive. So we can extend it by adding zeros, and that doesn't change the value, which makes sense. What if we have a negative number? 1, 0, 1, 1, 0, 0, 1, say, for example. So now this is negative 64, right? Plus, no 32s, plus a 16, 64, 16, 8, and 1. So what is that value? Well, it's 16 and 8, 17, 18, 19, 20, 21, 22, 23, 24, 25. So it's 64, negative 64, plus 25, which is 4 is 5, 14 minus 5 is 9, 5 minus 2 is 3, negative 39. That's the value. And we can verify that if we wanted to by flipping the bits, which is 0, 1, 0, 0, 1, 1, 0, and adding 1, 0, 1, 0, 0, 1, 1, 1, which is 1, 2, 4, 8, 16, 32, and that's 4 and 2 and 1 is 7, 39. So this is, in fact, negative 39. Great. How do we extend the size of this representation if we need it to fit in more bits rather than more than 7, right? This is in 7 bits now. If we want it to fit in 8 bits, how do we extend that? Especially thinking about the fact that this top bit represents a negative place value. Well, that's weird except you just do the rule that they taught you in class, which is just extend the sign. Now, that is a magical rule which will give you the right result, but why does it work? Well, because when you extend the sign, let's go back and just extend the sign one bit. This says negative 64, this says positive 32. When you extend the sign, what you're doing is making a new place value, and that top place value must have a negative value. That's what 2's complement means. So this is now negative 128, the next power of 2. And that means that this is no longer negative 64. Now it's positive 64. And what this did is it didn't affect any change in the value because we added a negative 128, but we went from negative 64 to positive 64, which is also positive 128. So it doesn't change the value at all to add that 1 there. We subtract 128 and we add 128 and everything is the same. So that's why you can sign extend as much as you want because it doesn't actually change the value. What about the biggest negative number and the biggest positive number in a representation? Let's start with a 4-bit representation. This is a 4-bit 2's complement number. The biggest positive number, now the rule, they just give you a rule, right? 2 to the n minus 1. Sorry, the biggest positive number is 2 to the n minus 1, and the biggest negative number is negative 2 to the n. All right, this is 2 to the 0, which is 1. Maybe I've got these numbers wrong. 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3. Right, so this is, I've got this wrong. 2 to the n minus 1, and the biggest negative number is negative 2 to the n minus 1. Those are our biggest and smallest values, but you have to think about it. Even I have to think about it because is it 2 to the n minus 1, where does the minus 1s go? It's messy. But if you think about it as this is negative 2 to the n minus 1, because this is 0, 1, 2, and 3, if this is negative place value, then it all makes sense. This is the only value that's negative, which means the biggest negative number is when you have a 1 here and all zeros, which is negative 2 to the 3, which is negative 8. The biggest positive number is when you have no negative value and all positive values, right? Which is 1 and 2 and 4 is 7, which is 2 to the 8 minus 1. So that's why the biggest positive number is 2 to the n minus 1, because it's all 1s down here. And if you add 1 to that, you get the next one up. And this is why the biggest negative number is negative 2 to the n minus 1, because it's the top place value, which is the only place where negative place values can go in. What about the fact that 1, 1, 1, 1, 1, 1, 1, 1 is always negative 1 in 2's complement? Well, again, if you take the top bit as a negative place value and the bottom bits as positive place values, then it all makes sense. This is 1, 2, 4, 8, 16. Now I've run out of space. Let's make a bigger picture of this. Right? 1, 2, 4, 8, 16, 32, say up to 64. Why don't we start with a 3-bit number? 1, 2, 4. If these are all 1s, if it's a 3-bit representation, the top bit has to be negative. Negative 4, 1, oh, out of space here. 1, 0, 0 is negative 4. 0, 1, 1 is positive 3. Positive 3 and negative 4, 1, 1, 1 equals negative 1. Well, let's sign extend that. Don't worry about this. Let's sign extend that. 1, 1, 1, 1. Well, now it's negative 8 and positive 7, which is negative 1. Well, let's sign extend that again. 1, 1, 1, 1, 1. Well, now it's negative 16 and positive 15. All right, that's 15, and you can confirm that because 1 and 2 and 4 and 8 is 15. So whenever you have 0, 1, 1, 1, any number of 1s, that's always 2 to the n minus 1, because if you add one more to these, 2 to the n minus 1, minus 1. No, and now I've run out of space again. Let's do that one more time. If you start with 0, 1, 1, all 1s, this is going to equal 2 to the n minus 1 minus 1, because all of these 1s represent value. This has no value. When you add 1 to this, you get carry, 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 carry all the way in and get 1, 0, 0, 0, which is 2 to the n minus 1. So that means if you have something like this, which is negative, because it's a 2's complement, so we have negative 2 to the n minus 1, and something like this, which is positive 2 to the n minus 1, minus 1, if we add these two together, these cancel out and we get negative 1, because that's negative 2 to the n minus 1. Negative 2 to the n minus 1. So all of this is to say that all of those rules and mechanics and formulations of 2's complement make sense if you think about the top bit of the representation being negative, the bottom bit of the representation being positive. Two more things. First of all, the bit at the top of the representation being the sign bit. Well, if it's negative, right, if this is negative 2 to the n minus 1, and this is all 2 to the n minus 2 all the way down to 2 to the 0, then the only way you can have a negative value is if you have a 1 here. Because none of these can add up to a value bigger than that. And the only way you can have a positive number is if you have a 0 there. Because if you have any numbers in here at all, right, if you have a 1 here, it's got to be negative. So you have to be 0, and then all of this are positive. So that's why we can treat that top bit as the sign bit. What about overflow? Last thing. Overflow also makes sense if you look at the top bit as a sign bit. So overflow. First of all, overflow happens when you add numbers together. Here, we'll look at 4-bit examples. Here's a 4-bit example. Here's 0, 0, 0, 1 plus 0, 0, 0, 1. 1 plus 1 is 2, right? 0, carry the 1, 1, 0, 0. That's 2. That's fine. No problems. What about 1, 1, 1, 1 plus 1, 1, 1, 1? Negative 1 plus negative 1. What do we get? 1 and 1 is 0. Carry the 1. 1, 1, 1 is 1. Carry the 1. 1, carry the 1, 1, carry the 1. Now in 2's complement, we ignore the carry when we're looking at the value, so we get negative 1 plus negative 1 gives you negative 2. Also, perfectly fine, right? This is 1, 2, 4, 8. This is 8, negative 8 plus 4 plus 2 gives you 2. That's fine. Two more possibilities. What if we have 0, 1, 1, 1 plus 0, 1, 1, 1? This is 7 plus 7. 1 and 1 is 0. Carry the 1, 0, carry the 1, 1 and 1 is 0, carry the 1, 1, carry the 1, 1, carry the 1, 1. 7 and 7 is not negative 2, so that's a problem. Fourth case, 1, 0, 0, 0, 1, 0, 0, 0. This is negative 8 plus negative 8. 0 and 0, 0, 0, 0. 1 and 1 is 0, carry the 1, which we ignore. Now we have negative 8 plus negative 8 equals 0. Also wrong. These are the 4 possibilities for adding 2 numbers together. And in 2 of these cases, they're wrong. And so we want to say overflow equals 1. We want to indicate overflow where the answer could be wrong because the value that we want doesn't fit in the representation. The number 14 doesn't fit in the representation. Right? The number negative 16 doesn't fit in the representation. So how do we indicate this? Well, again, if you treat the top column as a negative column, then it all makes sense because it all depends on whether you carry into the top column and also carry out again. If you carry a positive value into a negative column, that's weird, but if you carry it out again, it's fine. So in this case, there's no carry in, there's no carry out, everything's fine. In this case, you carry in, but you also carry out, and so it's fine. In these 2 cases, either you carry into the top column and don't carry out again, so there's a problem, or you don't carry into the top column, but do carry out, and so there's a problem. And in both of those cases, you have to indicate overflow to the computer. That's why overflow is calculated as the XOR of carry in and carry out of the top column. If carry in equals carry out, as in these 2 cases, everything's fine. If carry in does not equal carry out, as in these 2 cases, then there's a problem. So all of these techniques about 2's complement, using the top bit as a sign bit, calculating overflow, sign extension, all of these things make perfect sense if you understand the underlying theory that the top bit is a negative value, all the other bits are positive values. And that's how you understand 2's complement.